All right, so get ready because this deep dive is gonna be a wild one. We're talking about information density and temperature and how they're
It's
connected.
a pretty crazy concept, right?
Totally. It's like, how can something as simple as temperature be related to something as complex as information?
Well, that's what we're going to explore today. We've got a bunch of research here, articles spanning physics, thermodynamics, even some quantum mechanics and astrophysics. So,
Yeah, and I gotta say, even just glancing at these titles, it's mind-blowing. Like, does a colder system actually hold more information?
yeah, that's a big one.
And what about the role of heat in all of this? How does that play into how information is processed? It's fascinating stuff.
We'll even touch upon how these concepts play out in those really extreme environments, like the heart of a sun or the depths of a black hole.
Seriously.
Yeah,
Okay, so before we get ahead of ourselves, I think we need to lay down some groundwork. What exactly do we mean by information density?
right. It's kind of more than just data storage, like how many gigabytes you can fit on your hard drive.
Right, it's not just about bits and bytes, right?
Exactly. We're talking about how information is encoded at like the atomic level, like in the molecules.
So like the arrangement of atoms, the
Yeah,
bonds between them?
exactly. The structure of matter itself, it's about the potential for complexity and change within a system. Like how much information can be packed into a certain space, but also how that information is structured and how it can change.
Okay. So it's not just about how much stuff is in a given space, but about how that stuff is organized and how it can, like, interact.
Exactly. It's like, think about water versus a rock.
Okay, I'm intrigued.
Both of them, right? They have mass, they take up space, but they have different information densities.
Okay, yeah, I see where you're going with this. Water, it's always changing, right? It flows, it takes on different forms. But
Yeah.
stone, it's pretty much just, well, a rock.
Right. And that's the key. Water, with its hydrogen bonds, it transitions between state solid ice, liquid water, gaseous vapor. All those transitions, all those interactions, they encode information.
Yeah.
It can do all sorts of things like dissolving stuff, participating in chemical reactions, it's driving biological processes. Stone, though, it's got a rigid crystal lattice. It just doesn't have that same level of dynamic complexity.
Ah, okay. So even though a rock, might hold information about its formation over millions of years, water, because it's always in flux, it holds more potential for information in the here and now.
Right, precisely.
Okay, that makes sense. But here's where my brain starts to melt a little. You're telling me that even empty space, like the vacuum of space, has information density?
Yeah, it does.
What? How is that even possible?
Well, thanks to quantum physics, we now know that even a vacuum, it's not truly empty.
Okay.
It's teeming with these quantum fluctuations, all these virtual particles popping in and out of existence.
Mm.
So it's this very dynamic system with a baseline level of information encoded within those fluctuations.
Okay, so empty space. Not so empty after all.
Right.
All right. Now, how does temperature fit into all of this? Because I know our sources suggest that colder systems often have higher information density, which seems counterintuitive. Wouldn't more energy mean more information?
You'd think so, right. But it's not quite that simple.
Okay.
The key here is entropy. Think of heat as often implying disorder and increase in entropy. As things heat up, their molecules are moving faster and more randomly. Cold, on the other hand, often implies more order. Things cool down, those molecules slow down, they arrange themselves into stable and predictable structures.
Okay, so like ice, it has that super ordered crystal structure compared to water vapor where the molecules are just going crazy.
Exactly. Ice is a state of high information density but low energy.
Mm.
Steam, high energy but minimal structural information.
So where does liquid water fit into all of this?
Liquid water is right in that sweet spot, right in the middle.
Mm-hmm.
It has enough energy for those molecules to move and interact,
Yeah.
but it also retains enough structure to allow for some complex information processing. And, that's essential for life as we know it.
Ah, so our bodies needing to maintain a specific temperature are like the perfect example of this balance.
Exactly. Too hot, our cells break down. Too cold, our processes stop.
We got to be right in that Goldilocks zone.
Exactly.
Okay, so we've got water, we've got ice, but what about like extreme examples? What about black holes and the sun? They seem to defy this whole colder equals more information idea.
They do, yeah, which is why there's some interesting.
Okay.
Black holes, with their immense gravity, are incredibly cold in terms of emitted radiation.
Right.
But they're thought to have immense information density, all concentrated within the singularity in that event horizon.
Yeah.
The point of no return where not even light can escape.
Right.
Yeah.
So are black holes like giant cosmic refrigerators
Yeah.
just locking all that information away?
That's an interesting way to think about it. But it's more nuanced than that. The information isn't being processed or used in the way we usually think of it. It's more like it's paused, you know, like a quantum vault, holding potentially vast amounts of information, but it's inaccessible to us.
Okay, I think I get it. So black holes are cold and dense, holding on to a ton of information but not really doing anything with it. But what about the sun? It's a giant ball of fire. How can it possibly be information dense?
Well, the sun shows us how information can be encoded in processes, not just
Uses.
structure.
Okay.
All that heat.
Yeah.
It's from nuclear fusion, right?
Right.
And that releases huge amounts of energy and encodes information within the dynamics of those reactions, the interplay of all those particles and forces.
So it's like information is constantly being created and radiated outward from the sun.
Exactly. It's dynamic.
Okay, that's fascinating. So we've got these two extremes. Black holes hoarding information in a cold, dense state, and the sun radiating information as heat and light. It seems like we need to rethink how we view the role of heat in all of this.
Absolutely. What if, instead of just seeing heat as energy, we view it as information dissipation?
Wait, hold on. How can heat be information dissipation?
Think about what happens when something heats up. The molecules are going crazy, moving randomly. That increase in entropy, that randomness, it means there's a decrease in the information content of the system.
So the information's still there, but it's less organized, less useful.
Exactly, like
Yeah.
scrambling a message,
Sure.
right? The letters are all still there, but the meaning is lost.
Ah, so cold with its inherent order is like concentrated potential information, and heat with its inherent chaos is like diffused information.
That's a great way to put it.
Whoa, that is mind-bending.
Okay.
And it makes you think about the universe in a whole new way. Okay, we've covered a lot of ground here, but my brain needs a minute to process all this.
Yeah, it's a lot to take in.
So maybe we should pick up in part 2 with some specific examples of how this all plays out in the real world.
Sounds good. Let's dive into superconductivity and even our own bodies and how they're affected by this interplay of information and temperature.
Okay, so we've been talking about this wild connection between information and temperature, but how does this actually play out in real systems? Like, I know our sources mentioned superconductivity,
Oh yeah, that's a great example.
but what's so special about it?
Well, it's a perfect illustration of how, like, lowering the temperature can dramatically increase information density and processing power.
Okay.
At super low temperatures, some materials, they have zero resistance to electrical current.
So it's like a perfect electrical highway, no energy lost as heat.
Exactly. And the reason this happens at those crazy low temperatures, the electrons in the material pair up and they move in this, like, super coordinated way. It's like a perfectly choreographed dance, you know? Each electron knows exactly where it needs to be, how to move without bumping into anything.
So it's like they're all working together.
Yeah. And that level of order lets information, like in the form of electrical current, flow through the material with zero loss, no distortion.
So by chilling these materials down to those extreme temperatures, we're basically getting rid of the randomness, the entropy.
Right.
And that's what allows this amazing information flow.
Exactly. And the applications, they're mind-blowing. Like imagine lossless power transmission,
Whoa.
lightning-fast computers, maybe even levitating trains, all because of that connection between information and temperature.
That's incredible. Okay, but let's bring it back down to earth a bit.
Right.
What about like biological systems?
Mhm.
Our sources talked about how information and temperature interact in living things.
Oh, yeah, it's a fascinating.
It's kind of a paradox, isn't it? Like life is this super complex, information-rich phenomenon,
Right.
but it exists in this tiny temperature band, constantly battling against, the tendency towards disorder, towards entropy.
It is a constant battle.
So our bodies are basically information processing machines that use energy to maintain their structure, their function,
Yeah.
but also have to fight against this heat-driven degradation.
It's a balancing act, really.
Okay.
We need enough heat to power the chemical reactions that make our metabolism work, keep our cells alive.
But too much heat and everything falls apart.
Yeah, those delicate information structures in our DNA, our proteins, they start to break down.
So it's like we're constantly trying to maintain this specific level of information density, not too high, not too low, so we can stay alive and function.
Precisely.
Wow. And this applies not just to us, but to entire ecosystems, right?
Oh, absolutely.
Like different species have evolved to thrive in all sorts of different temperature niches.
Right. And what's really interesting is that, like, the diversity of life, the richness of information in an ecosystem, it's often directly related to the amount of available energy.
So like a tropical rainforest with all that sunlight and warmth,
Yeah.
it can support way more variety of life than, say, like a frozen tundra.
Exactly. It's like the heat provides the fuel for evolution to create those complex information-rich systems.
So are we saying that to get complexity, you need to find that sweet spot, that Goldilocks zone, where there's enough energy to drive processes, but not so much that it, like, overwhelms the structures that hold information?
That's a great way to put it. It's not just about temperature,
Okay.
It's about that balance, energy, and order where information can be encoded, processed, transmitted efficiently.
Right.
And that understanding, well, it could be key to like everything from tech innovation to how we deal with the environment.
Right. Okay, I want to circle back to this whole heat as information dissipation thing.
Sure.
Can you give us a real-world example?
Let's think about a campfire, right? You start with wood. It's got all this stored chemical energy and information locked up in those molecules.
Okay, and then you light it on fire. All that energy is released as heat and light.
Exactly. And as they burn, that structure breaks down. Those molecules get transformed into simpler stuff, carbon dioxide, water vapor.
So the information in those complex wood molecules, it's basically being dissipated.
Yeah. As those molecules break down and release their energy as heat, they become less organized, less accessible.
So the information isn't destroyed, but it's like spread out, less useful.
Exactly.
Whoa, I've never thought about it like that.
It really makes you think about how we use energy, right?
Definitely. So are you saying that every time we use energy, we're basically spreading information out into the environment?
Yeah, as heat, like driving a car, powering our homes.
Yeah.
It's all information dissipation.
Wow. This is giving me a whole new perspective on, like, everything. Okay, so we've gone from atoms to black holes, and we're starting to see how information, energy, entropy, it's all connected.
It really is.
But what about the bigger picture? What does all this mean for the future?
Well, if we can figure out this dance between information and temperature, if we can learn to really control it, the possibilities are huge.
Like what?
Imagine harnessing the information density of the vacuum itself. We could tap into a near infinite source of energy.
Whoa. That would solve so many problems.
Right. And think about communication. If we could use quantum entanglement.
That spooky action at a distance thing.
Yeah. We could send information across huge distances instantly.
Faster than light communication.
Exactly. And then there's computation. Quantum computers running at those super low temperatures we talked about. They could do calculations that normal computers can only dream of.
So we could have breakthroughs in, like, medicine, materials, AI. The possibilities are endless.
Exactly. But it's not just about technology. This could revolutionize how we think about sustainability.
Okay, how so?
Well, by understanding how energy use dissipates information, we could design systems that are way more efficient.
So instead of just thinking about energy efficiency, we'd be thinking about information efficiency.
Exactly. It's a whole new way to approach sustainability.
This deep dive has really opened my eyes. We've gone from the structure of water to quantum computers and even rethinking the very idea of heat.
It's all connected. And we're really just starting to scratch the surface.
So much to explore.
So much potential.
All right, we're going to take a short break, but when we come back, we'll keep going. We'll talk about the implications of all this, how it could change the future. Stick with us.
All right, welcome back. My head's still spinning after all that talk about information and temperature. It's incredible how this connection just seems to touch everything in the universe,
Yeah, it's like we started with atoms, then black holes, and
Yeah.
it's clear this relationship is everywhere.
Totally. So where do we even go from here? I mean, we've talked about some pretty wild stuff,
Yeah.
like harnessing vacuum energy,
Yeah.
instantaneous communication.
Mm-hmm.
Is any of that actually possible?
Oh, that's the big question, isn't it? I mean, we're still figuring out this whole dance between information and temperature.
Right.
But I think the potential, it's massive. Think about all the scientific revolutions that came from, like simple insights, gravity,
Right.
electricity, the atom.
Mm.
We could be on the edge of something huge here.
So you're saying this could be the next big scientific revolution? I think it has the potential, yeah.
Yeah.
And it's not just about theory, This knowledge could lead to real changes, like in technology, medicine, energy, everything.
Okay, let's get specific. What are some of the most promising research areas that could really turn this knowledge into something, real?
Quantum computing, definitely.
Right, we talked about those earlier.
Yeah, they operate at those super low temperatures,
Yeah.
taking advantage of quantum mechanics to do these insane calculations.
So by basically harnessing the cold, we're unlocking the power of quantum information processing.
Exactly. And the things we could do. Amazing, like designing new materials atom by atom, simulating those crazy complex biological processes, even developing AI that could, like, surpass us.
That's wild. What about tapping into vacuum energy? Is that even remotely possible?
That's a tough one.
Yeah.
The theory's there, but the challenge is how to actually interact with those quantum fluctuations,
Hmm.
to actually extract usable energy.
So it's like the energy is there, but we just can't grab it.
It's like trying to build a windmill in a hurricane.
Oh, I like that analogy. Lots of energy, but super chaotic.
Exactly. So we have to tame that quantum chaos. And that's where understanding this whole information temperature thing is so crucial.
Okay.
We need to figure out how to create order in that chaotic system.
To like channel it.
Yeah.
Yeah.
To channel those fluctuations into, a predictable energy flow.
Sounds like a huge challenge.
It is.
But the payoff.
Oh, it would be massive.
Hmm.
We're talking about potentially solving one of humanity's biggest problems.
Sustainable energy.
Exactly. But, we've talked a lot about the good stuff.
Right.
But there are also risks that come with this kind of knowledge.
Oh, okay. What kind of risks?
Well, like with any powerful technology, there's potential for misuse, right?
Mm.
Imagine if someone could manipulate this information temperature relationship to, like, mess with biological systems
Whoa.
or even change the climate.
Yeah, that would be bad. So we
Well,
need to be careful.
very careful. Ethical considerations, they have to be front and center with all of this. We need to be talking about the consequences, setting clear guidelines for how we use this knowledge.
I agree. Okay, so this has been quite a journey. Atoms, black holes, rethinking heat itself.
Yeah.
It's all about information and temperature. So for our listeners, what's the main takeaway here?
I'd say look at the world a little differently. Think about the information hidden everywhere. In the structure of stuff, the way energy flows, that balance between order and chaos that makes life possible, it's all tied together by information and temperature.
And remember, we're part of that web too, right?
Absolutely.
The choices we make, the way we use energy, the technology we develop, it all affects the information content of the universe.
It's a huge responsibility,
Right.
but it's also a huge opportunity. The more we understand about this fundamental relationship, the more we can unlock the secrets of the universe and build a future that's both sustainable and awe-inspiring.
Well said. Thanks for joining us on this deep dive into the world of information density and temperature. Hopefully you've come away with a new appreciation for the hidden connections that tie everything together and the power we have to shape the future. Keep exploring, keep asking questions, keep pushing the boundaries of knowledge. Until next time.